Okay, thank you for having me. Yeah, great to be back here. So I'm going to talk about a new paper that we just put on arXiv yesterday. So brand new on recurrent nets. So it's going to be on pre-training recurrent nets without recurrence. And this work is led by my student Akarsh, who is somewhere here. Akarsh, raise your hand. Okay. So I'll be directing all the questions to Akarsh. So get ready, Akarsh. Okay. So this project actually goes back to an interest I've had for a long time, my first paper in grad school back in 2011, where I was interested in why do people remember some images better than other images. So we ran these experiments where we'd show participants in the study a sequence of images, and every now and then one of them would repeat, and they would have to click a button when they saw a repeat. And there was a striking finding that some images are just not remembered well at all, the ones on the left, and some images people will always remember. And in particular, this guy right here is the most memorable image that we ever found in all our years of study. Anybody have seen this one before? I've given this talk. I give this talk every few years. Okay, anyone recognize that guy? No. Well, maybe you'll remember him in the future. But I just think that this really is still an open and hard problem. Why is it that our brain is able to record these in memory and it doesn't record those in memory? You would think that the hard part about memory is that a memory is not going to be useful until sometime in the future. So somehow my brain anticipated that I'm going to give a talk 15 years later, and it's going to be useful for me to have remembered this guy so I can put him in the talk and tell you an anecdote about that guy, right? Like, how did my brain do that credit assignment problem over 15 years? It just seems impossible. Okay, so I think that AI is still lacking a good memory mechanism. I think this is still an open question. You might remember this paper, Attention is All You Need, to introduce the transformer. And I think that title was in reference to saying, you don't need memory. Because at the time, people were having these memory networks and thinking you need to record information into memory. And then that paper said, no. All you need is just remember everything in a big tape and attend to the stuff that's useful at any given time. Okay, so we're in this era of attention is all you need. But I don't think that's going to cut it. Life is very long context. We can increase our context window for our transformers, but eventually we're going to run out of memory. We're not going to be able to have a context, I think, that goes across an entire agent's lifetime for many years. This workshop is on world models and social intelligence, and I think this is a place where effective intelligent memory is especially important. We need our understanding of the world to update and be adaptive over time. We need continual learning. We need something that can change, a representation of the past that can change when new information comes in. Okay, so AI needs compressed, because our life is long context, and continually adaptive because the world changes memory. Okay, and so the current main solution, transformers, are not sufficient because they don't compress the past. Attention is all you need. They just record every past token or thing that you observe into this thing called the KV cache. Memory works by just concatenating and extending this in an unintelligent way. Okay. There is a modern solution, which I think would be fun to debate about. This might actually be sufficient, in my opinion. The modern solution is that you handle memory at a higher level of abstraction. You have agentic AI systems that read and write files, markdown files. I'm not going to talk about that. I'm going to talk about really solving this from the ground up. And we actually already had this solution. I think everybody knew that that recurrent neural networks were the thing that would eventually have to come back. They were a very good solution. They just solved the memory problem from the ground up. They have a memory state that gets updated when new information comes in, and they train the entire thing to encode into memory a compressed representation of the world that updates. Okay. So here's the problem of memory. We have the past, and we have the future. And in this cartoon, this guy is putting the apple into the box. He has to remember that there's an apple, so later he can come back and eat that apple and get a reward. And the fundamental problem is that you need to record information that won't become useful until much later in time, maybe years later in time. Okay, so how do you know which pieces of information are going to be useful in the future? And this is called the credit assignment problem. Okay, somehow I have to assign credit to that memory of putting the apple into the box so that I can use it later. Okay, so here is how RNNs deal with memory. I think it's just a beautiful idea, modeled on how we think the brain works. So you have a kind of fixed representation in your head somewhere, a vector or some kind of tensor, and every time step you record information into that memory, and you update from one time step to the next in incremental fashion. And the problem is the credit assignment problem, that in order for me to know to encode this apple's location into that memory state, I only will find a use for that later, and I need to assign credit to this recording action from this reward up here. So there's this long temporal dependency between the two. And it's t steps long, where t is the number of time steps, which over a lifetime might be a trillion, right? How many seconds have you been alive? How many milliseconds have you been alive? Okay, and this credit assignment problem is confounded by all the intervening events, all these spurious associations. Maybe a bird flew around in the background, and it was the bird flying around what made it so that I could enjoy the apple later? No, that's just a spurious correlation. Okay. So the standard approach to solving this is called backprop through time. So backprop through time just says I will do gradient descent over this computation graph to eventually, propagate my gradients back. I got a reward here, and then I figure out what I had to wiggle earlier in time in order to increase that reward. And this is difficult because it's a t-step temporal dependency problem, and backprop through time has all of these problems due to this long computation graph. Okay, so the first problem is that it's unstable because the computation graph is long, t steps. Backprop uses the chain rule. You're multiplying each of the steps as one gradient term in that chain rule. And this is like taking a matrix, which is the gradient of one recurrent step, and like raising it to a high power. It might explode or it might vanish. In the stochastic mini-batch setting, this is high variance. I'm trying to estimate how I wiggled something like 10 years ago in order to produce an effect 10 years later. It's a very hard to estimate gradient. Okay. That's problem number one. This is like the fundamental kind of statistical challenge of backprop through time. There's also a computational challenge, which is that backprop through time is sequential. What that means is you can't run it efficiently on a GPU. Okay, so one gradient update requires t sequential steps of computation, where t is the time horizon. Okay, and transformers became really popular more, I think, due to the second item than the first item. The second item for transformers, they're fully parallel. They don't have any kind of sequential dependency over time when you train them. They're fully parallel. Okay. So there's many attempts over the years to remove backprop through time. There's a lot of ideas in reinforcement learning where you would learn value functions and bootstrap up from those. There's ideas in gradient-free and evolutionary optimization. None of these have really stuck around for training recurrent networks. So still backprop through time is the de facto thing that we use even today. There are a few really recent works like this next latent prediction method that I'll highlight, which is very, very similar to what I'll present next. Okay, and there's also another option that people have thought about, which is say, training nonlinear RNNs is too complicated, backprop through time is too complicated. Why don't we just only use linear RNNs? But I don't think that's not our original goal. We don't want to have a memory mechanism which is only linear. This is much less expressive in some sense. Okay, so we are trying to solve this or replace backprop through time in this paper. So our questions are, can we train an RNN without backprop through time? Two, even more extreme, the fundamental error with backprop through time is you're rolling out sequentially over time and then backpropping through that chain. Can we train an RNN without ever even rolling it out at all? Okay, rolling it out means rolling the recurrent operation out t steps in time. And somehow can we supervise this credit assignment problem over t sequential steps with some kind of credit assignment problem which is fundamentally shorter, in fact, over just one computational step. Okay. So here is, again, the diagram of how RNNs learn to remember things. And the observation I want to make is that if you consider this memory token right here, its job is to take all the information from the past that is going to allow it to make predictions about the future, if the goal is to reconstruct or predict the future. And that job can be stated in a way that's kind of independent of the mechanism that arrives at this representation. We can say, what is the optimal representation of the past for predicting the future? And just write that as a general, like, let's find the form of that solution. And we don't have to use an RNN to find that solution. We know what the kind of we know what the ideal solution is. It's a predictive state. A representation of the past is sufficient statistic of the past for predicting the future. And so we can instead estimate that predictive state with a different computation. Okay, we're searching over how can I possibly encode the past into a vector that's predictive of the future. We can search over a different hypothesis space, not RNNs, but a different architecture. And this will give us the form of the solution, and then we can have our RNN try to imitate that ideal solution. Okay. So the point is, by changing our perspective in that way, now the credit assignment problem doesn't go through any updates to our memory state. So we're just gonna call it a one-step credit assignment problem. There's like a shortcut connection between this item in the past and where I got reward for it in the future. Okay, these arrows are universal function approximators, let's assume. Like maybe they're at infinitely wide MLP. Okay, but it's still just one step, another step. It doesn't depend on t. It doesn't depend on the time horizon. Okay. So to formalize that just a little bit, maybe that we can have some fun discussions with theoreticians about like proving exactly when this should work. Encoding what you should remember for the purpose of predictive state is time parallelizable. And the reason is because any sequence, x1 through xt, can be reparameterized as a set of time-stamped elements. And the set is a permutation invariant representation. So memory is a mapping from a sequence of events to a memory state M. And this can be equivalently represented as a mapping from a set of time-stamped events to that memory. And if we search over what is the optimal memory under this parameterization, that search process can be done in a time parallel way. In particular, we can use an encoding of the past, which is a transformer, which is the most popular time parallel architecture. Okay, so sequential credit assignment through the encoder is not actually necessary to identify these optimal memory states at any given time. And another way of describing that is we're going to train this set to vector mapping to be a predictive state representation, a sufficient statistic of the past for predicting the future values of the sequence. Okay. So once we've done that, now we can just repeat the process at every single time point. So the optimal memory for predicting the future is this vector at this point. At this point, it's another vector. I'll keep on moving that along, and eventually I get a sequence of here's what would be the best thing to remember at this point. Here's what would be the best thing to remember at this point, and so on. Yeah, question.
In a way, this is very different from the memorability issue, because I would expect you to remember things that happen frequently, and therefore you want to have a short way of remembering them. Whereas the memorable images are not ones that I would expect to be frequent. These are actually outliers or salient ones. And those are the ones we memorize, actually, not the frequent ones.
Okay, this is a good point. So the human memory system is probably somehow adapted to a task other than just predict every event of the future. And maybe it cares more about rare events because they're somehow more meaningful or it's correlated with things that actually matter for tasks. So I don't want to say this explains a full human memory system. There's probably more to talk about there. But if I just want to model a sequence and maximize likelihood of the next item in the sequence, this is a good idea. Alyosha?
Why do I care about it being parallel if we live sequentially and we make memory sequentially?
Yeah.
Why do I need to worry about parallelism?
So parallelism is simply for training efficiently. So GPUs are parallel, and fundamentally, if you can train a system in a way that's time parallel, then I can just distribute it on a lot of nodes. The wall clock time is constant. So parallel is just to make it efficient on kind of hardware. Yeah. Okay, so now I've told you a mechanism by which we can get a kind of oracle sequence of what I should remember at every state in time for the purpose of predicting the future. But I haven't shown you that an RNN can achieve that. So the second step to our method is we'll just train an RNN to try to imitate that oracle sequence. Okay, this is training a memory updater. We already know what I should remember, and we'll train a memory mechanism that updates in the RNN fashion, where it only attends to the previous memory state, gets a new observation, and updates. Okay? So here's the method. We're going to use a time parallelizable predictive state representation to learn what I should remember. Okay, that's just an encoding of the past into a compressed fixed representation that predicts the future. We will do that at every time step, t, t+1, t+2, and so forth. This gives us our kind of optimal trajectory of memories that I should have, and we'll just behavioral clone this. So we're just going to train an RNN to, at any given memory state, given a new observation, predict the next memories, the next oracle ideal memory state. Okay, this is, in some literature, it's called behavioral cloning of that trajectory. Okay, so this is a one-step prediction problem, no rollout at all. You don't have to roll out in time. At every given state, you just predict one into the future, and you penalize the difference from the ideal trajectory. This is time parallelizable, so the whole thing is parallel in time with no rollouts at all. Okay. So can you train an RNN without backprop through time? Yes. Can you train it without rolling out? Yes, that's true too. Can we supervise credit assignment over T sequential steps with a kind of surrogate objective that just does it over one step? Yes. Okay. So here's the concrete architecture that we came up with. We call this supervised memory training. Okay. So the idea is that the RNN will have it's doing supervised learning on the sequence given by this oracle time parallel encode decode mechanism. So this is the sequence in X going from X1 to XT. Then we will encode that into memory. We will update the memory with XT+1, and that should match the encoding of the sequence in the future going from X1 to XT+1, okay? And the memory is trained to predict the future. So this part of the architecture learns a predictive state representation. This part of the architecture learns this is the RNN, this is the recurrent update loop. And if you train these things jointly, this encourages the memory to be Markovian. It should be, the next memory should be predictable from the last memory. And even more than Markovian, it should be functionally predictable, like whatever function approximator we use should work. And credit assignment now is constant length. It doesn't depend on t. Okay, so if you look at the backprop in this graph from a future time point to a past time point, there's only one step through the updater. There's not t steps through the updater, so it's constant with respect to time. Okay. So the key idea is we're decoupling learning what I should remember from how to update memory. I can define what I should remember, and then I can try to imitate that with a one-step predictive model. Okay, so just to put them side by side, BPTT rolls out the RNN and applies this update mechanism over and over again through time, and then backprops through the entire graph. Here we've kind of scrunched the future onto the left side of this graph, and that avoids this dependence on t. Okay, so this, we could stop here. That's the whole method. Turns out there's one detail which I think is a detail. Akarsh says this is fundamental and like a big contribution of the work. The detail is that if I am, so we call this supervised memory training. If I am simply behavioral cloning this trajectory of memories, that's a one-step prediction problem, but my errors can accumulate and I can drift. This is a well-known problem in kind of behavioral cloning in reinforcement learning or robotics. And so when I start to roll out my predictions autoregressively, like predict on top of my previous prediction, I'll drift away from the oracle memories. Luckily, we have a lot of methods to solve this. This is the general problem that you encounter when you're trying to imitate an expert. And one idea is called dagger. Another name for that is on-policy distillation. But essentially, these are methods that go under the family of post-training methods. So supervised memory training, think of that as like pre-training the RNN to have roughly good behavior. And then you need to roll it out on policy, see what happens, and penalize the differences from what you really wanted. And that's the family of post-training methods that can be fairly lightweight. So we're going to say you have to do some lightweight post-training. In practice, we use this method called Dagger. OK, so let's see if this actually works. So I like that Jack mentioned Atnev as one of the originators of world modeling. So I'm going to claim this is a world model. So this is Atnev's cat. He was saying, imagine that you're trying to predict the pixels. You're an ant walking across in raster order over the surface of this image of the cat. You're trying to predict what will happen next. How would you do that? So this is the ant, and this is what it sees. This is like the serialized raster order of this cat image. That's the sequence that we're modeling. And it's a hard problem because you have to remember a lot. When you see the first stroke, you have to remember a stroke began, and then a whole row later, you can figure out what was the angle of that stroke. And a whole row later, maybe you figure out what the curvature of that stroke is. A row of pixels is 32. The rows are 32. It's 32 by 32 image in this case, or roughly. Okay, and then way down here, I have enough information to say, oh, I get it. I'm looking at a cat. And then over here, maybe I realize that I'm at the end of the cat, and something else might happen. OK, so this is a hard memory problem. You can imagine the ideal memories might look like this. You're kind of recording that I created a stroke. Now, what was the stroke's angle, and so forth. OK, so I'll show you the cat result in a second. We benchmarked this on MNIST digits because it's just a simpler standard benchmark. This is pixel raster order sequential generation of MNIST digits. And the two curves are BP through time trained RNN on the top. It produces images that look like that. And our method down here produces images that look like MNIST digits. And just to show you what that looks like, this is how it generates an image, pixel by pixel. It's saying, OK, I'm making an 8. I have to remember that I made a first loop of an 8, and so forth. OK, this is a very long-range memory problem. OK. So here's what happens if you train this on a data set of sketches. Thank you, Alyosha, for this suggestion. And you run it on the cat. And OK, we're not quite there. There's a ways to go. But this is a really hard memory problem. Like, I guess the last row is probably the most good-looking row. It reads into memory the first, like, 3/4 of that cat. And then it has to kind of know the shape of the cat so it can continue these lines. And it's doing this as a several hundred. It has to remember information over several hundred time steps because there's several hundred pixels before you get to the bottom of the cat from the middle of the cat. OK, up here it only saw the top of the cat and it doesn't really know what it is. It thinks it's a weird flower or something else. Yeah, Daniel.
Where does the variability come from? What is the source of uncertainty?
The source of uncertainty is because we are still running this autoregressively at inference time. So you will predict the future, and then you'll take the next token that you predicted, the next pixel you predicted, and update your memory with that pixel. So it's run autoregressively. Yeah.
Stochastic or?
And that's stochastic, yeah.
Oh.
So it's the same as an autoregressive transformer. You have
These are tokens and you sample
over the tokens, yeah.
Does that mean that error accumulates?
Yeah, so error will accumulate during that sampling process. And then this DMT thing is supposed to, during training time, minimize that error. But you probably still have some accumulation of error, which you can kind of see down here.
What's the training data here? Is it just that, is it many sketches?
This is the sketchy data set. So it's many different sketches. I think I hid that. It's called sketchy, yeah. It's these kinds of images.
Has the model seen that like specific cat in training before, or
No,
okay.
yeah. Atnev's cat was not part of that data set. OK, so you can also investigate what the memory representation looks like. So the colors are it's the first 3 components of a t-SNE projection of the memory state. The memory state is it's a high-dimensional vector, roughly. It's actually a few vectors, but anyway, it's a high-dimensional vector. And you project that down into 3 dimensions, and you give those colors. So it's one of these like representations of features as colors. And now this is saying the memory changed right here. So what happened is because right at that location, it corresponds to like around here. And it kind of realized, oh, it changed its representation of what I'm looking at. It decided I'm looking at a cat. Okay, 5 minutes. Okay, so we are getting this kind of representation of the world that's growing over time as it's learning what it's looking at. Okay, so we can also investigate the structure of these memories using a few synthetic tasks. I think that I will. Yeah, I'm gonna skip ahead a little bit. Okay, I think I wanna share this one. So I think one of the really interesting things here is that we've always had this idea that we should learn the optimal compressed representation of the world. That should somehow be a good representation. And this can be a kind of a new scaling axis for where we can spend our compute. Okay, we fit the whole internet. We fit the data, right? And the companies have used as many tokens as I can stomach at test time. Right? I can't wait longer for ChatGPT to give me an answer. So we've done test time scaling, we've done training time scaling on fitting the data. And now we have all these NVIDIA GPUs and all these excess tokens. What are we going to do with them? And so all the companies are saying we're going to do recursive self-improvement. We're going to just start using loops and letting them go and just invent new things. But there's another option. You can spend your tokens on compression. Okay, so, but these ISO curves, this is flops versus a compression level, and the ISO curves are for a fixed performance in terms of next token likelihood. So if you look at one single curve here, that's saying that to achieve some modeling capability, I can expend more flops to get a smaller memory state, and this is just an idea for what you can spend your tokens on when you have excess ones. This is more for the industry people in the audience. Okay, so some limitations of this approach. So predictive state is only the right representation for some problems, not all problems. Okay. It's a good representation for predicting future elements of a sequence. And this entire thing is supervised by a time parallel teacher, which is a transformer in this case. Can you go beyond the limits of that teacher? And I think this comes back to this question, like, I don't think that I backprop through time or formed a memory association between this guy that I saw 15 years ago and this talk today where I'm reusing him. I think my brain came up with some heuristic, some rule that generalizes. This is a rule for a heuristic for what I should write into memory that might, predictably be useful in the future. And you see that the RNN is learning something similar. So here is an RNN that's trained only over sequences of length 64. And the teacher, if you go to sequences longer than length 64, doesn't work as well anymore. But the RNN has learned a recurrent update rule, something that generalizes over time. And so it does learn something that outperforms the teacher when you apply it to remembering longer sequences. It learned a heuristic, which actually generalizes further into the future than the teacher directly supervised. Okay, so the summary is RNNs are just like, they're the right model. They have to come back. SMT trains RNNs in time parallelizable fashion with stable gradients and constant length credit assignment. The key idea is to decouple learning what to remember, predictive state, and how to update memory, predict the next predictive state. So you can train an RNN without the R, and it behaves like an RNN. It exhibits generalization over time, and it learns heuristics for what to read and write to memory. So thank you, and feel free to ask Harsh questions.
Let's do one.
Okay, one question. Michal, okay, I'll have to go to the back there.
What do you lose compared to RNN? What's the catch?
So what do we use for?
Like RNN, you spend much more compute to compute the same thing.
Right.
Like I would expect it to be like some loss of some capabilities compared to an RNN.
Yeah. So that's exactly what this memory access is. So you have the RNN is not only the transformer just has to predict the next token with infinite memory. Here we have to predict the next token with finite memory. That's a harder problem, so we have to spend more compute to solve that harder problem. So what you lose is if you don't spend that extra compute, you do worse than the transformer. So compression takes extra flops. That's the trade-off.
Thank you.
Okay, I guess we have to.
All right, thank you so much.
Okay, thank you.
We have a coffee break now. We'll be back at 11. ahead, Michaela.